Hello, and welcome to the Fibre Channel Industry Association. Today we're going to be talking about something that's been on a lot of people's minds, NVMe over fabrics using Fibre Channel, otherwise known as FC NVMe. Our agenda today is really jam-packed. There are a lot of people out there who are curious about this, and they come from all kinds of backgrounds. So for that reason, we're going to be providing some basics when it comes to Fibre Channel and NVMe, before discussing how the two intersect with FC NVMe. So obviously, due to time constraints, we're not going to be able to go too far in depth, but we are planning on going into a much deeper dive in a later webinar. For now, though, we'll not just talk about FC NVMe and how it works, but also why someone might want to actually use it. Today, my name is Jay Metz. Actually, my name is Jay Metz every day, but today we're going to be talking. No, it's just one of those things, right? Humor in the webinars. And I have another member of the board of directors for FCIA, Craig Carlson, who also just so happens to be the chair of the T11 FC NVMe committee. So we are both intimately involved in FC NVMe. Now, before we get started, let's just get everyone on the same page. So this is the first webinar on FC NVMe. So we're going to be starting with some reminders of how the technology works before discussing an overview of how they work together. And it also may be useful to know that these slides will be made available after the presentation at fibrechannel.org. We also highly encourage you to ask questions. Now, if we have time, we'll try to answer them during the webinar. But in case we run out of time, we're going to be answering the questions on a blog as soon as possible after the presentation, and there will be links to this at the end of the presentation, so stay tuned. So, even though we have a lot of material, we're simply not going to have the time to go too deep into the bits and bytes here. There are other webinars on NVMe and NVMe over fabrics, and for those of you who really want to get into the nitties and the gritties on FC NVMe, we will be presenting an even more thorough in-depth webinar later on. So if you're a standards geek or a real tech head, we're going to be giving you a lot of material over the course of these different webinars. So with the preliminaries out of the way, let's get started with a crash course on Fibre Channel and help set the stage. Craig?
Okay. So I'm sure a lot of people out there are familiar with Fibre Channel, for those of you who are not, sort of an overview of what is Fibre Channel. Fibre Channel is a purpose-built network for storage. Unlike Ethernet, which is a purpose-built network for everything, Fibre Channel is a purpose-built network for storage. The Fibre Channel fabric has a physical connection between each host in a storage, and that connection may go through a fabric, but there is a physical connection between each device. There's also a logical connection between each device, and a logical connection can always be made. There is no blocking in a Fibre Channel fabric, and that's one of the key design aspects of it. Some of the design requirements for a Fibre Channel SAN, the goal is to find one-to-one connectivity, and that's what I talked about. There's no blocking. There's always access to any other device. There's also a transport and services layer, and this layer it's a very thin layer, and it pretty much rides in at the same frames as the Fibre Channel data. There are well-defined end device relationships. There's initiators and there's targets. Initiators are the hosts, and targets are the storage devices. And it also does not tolerate packet drop. It's a lossless transport. And in the Fibre Channel fabric, there is only north-south traffic and no east-west traffic to speak of. And that means that primarily the traffic direction is from initiator to target, and then from target to initiator for responses. The network is also designed for scale and availability. Fibre Channel is a highly available network topology. Data is spread throughout the fabric. There's no single point of failure within a Fibre Channel fabric. There's also a edge-to-core service relationship. It's like the fabric provides the services, and such the fabric is the controlling aspect. So some of the design elements in a Fibre Channel fabric, as I already mentioned, is the host and the target. And those talk through a fabric or a switch. So the Fibre Channel Initiator is a host system that has a Fibre Channel adapter, which is called an HBA, or a host bus adapter. This is equivalent to a NIC for Ethernet. And this is the point where protocols such as SCSI or NVMe are encapsulated and then transmitted in a Fibre Channel frame. The other big part of the Fibre Channel fabric is the switch, and all the intelligence for the fabric is contained in the switch, and one of the most important components is the name server. The name server is a repository of all the information regarding what ports are connected and what they can do. It's also important to note that the Fibre Channel name server is implemented as a redundant distributed database. It's not contained in one device. It's spread out through all the switches in the fabric. So if one switch goes down, that information is still available. Components like HBAs and targets can register the characteristics of the name server, and this means that the name server knows everything that's going on in the fabric. Some discussion points about the Fibre Channel protocol. The protocol uses what's called a unacknowledged datagram service. In Fibre Channel terminology, this is called Class 3. Excuse me. Class 3 is defined as a reliable datagram, and that means that it will not be dropped unless some sort of error occurs, such as a bit error or some other unrecoverable error that could occur in the fabric. Now, this doesn't happen very often. It can happen, but it really doesn't happen very often. So it really is a drop or a lossless connection. So for Fibre Channel data, there's three constructs. Frames, which is a packet of data. Sequences, which is a set of frames for larger data transfers. And exchanges, which is an association of sequences and frames that make up a single command. So a single frame can be up to 2112 bytes, and it contains a Fibre Channel header, a payload, and a CRC. And the CRC provides a data integrity check on the header and the payload. If anything is corrupted in either the header or payload, the CRC will detect that, and the frame can be discarded. Frames are bundled into sequences. A sequence can contain any number of frames, and allowing possibly up to multi-megabyte data transfers. And then sequences can be bundled into exchanges, and many protocols, including SCSI and FC NVMe, use an exchange for a single command response. And an interesting thing about exchanges is that while individual frames within a single exchange are guaranteed to be delivered in order, exchanges themselves may be delivered through different routes in the fabric. This allows the fabric to find the optimal route for any particular exchange, or in the case of FC NVMe, any particular command. So if one particular route through a fabric is congested or blocked, then the commands can choose a different route. And of course, in any network, you need to have some way of discovering what's going on. And as we already mentioned, the method of doing that is the Fibre Channel name server. The name server contains information that is automatically registered, such as worldwide names, protocol types, protocol features. Every single port in a Fibre Channel fabric has what's called a worldwide name, which is a worldwide unique identifier, usually assigned in the factory. This is similar to a MAC address if you're familiar in the Ethernet world. And there are two types. There's the worldwide node name, which identifies the devices, and the worldwide port name, which identifies each port in a device. Fibre Channel also has a concept called zoning. Zones add a level of security by allowing the switch to control which ports are visible to each other. It's also important to note that these zones can be changed frequently in such as a case where you might have a backup that runs at night, and you want the backup port to have visibility to all the ports in the fabric, and then during the day when it goes back to normal operation, it only has visibility to its normal subset. The other thing, important thing about zoning is that zoning is implemented by the switches in the fabric. Zoning is similar to ACLs and Ethernet switches, but the difference is that in zoning, the fabric is a central point of authority, which means that the zoning database is distributed through all these switches, and all switches have the same view of the zoning configuration. And the zoning is also standardized, so all devices understand what the view is. So a little bit on the Fibre Channel protocol layering. Fibre Channel has defined in layers similar to OSI and TCP. And briefly, we have a physical interface layer, which is the photons, electrons, byte encoding, framing, common services, and then the upper layer protocol interface. And that's the interface that protocols such as SCSI, FICON, and NVMe are defined on. Okay, so FCP. What is FCP? The term FCP goes back to the beginning of Fibre Channel, and historically it really meant SCSI over Fibre Channel. But recently, other protocols have started using FCP as well as a data transfer protocol. And FCP is now being used for FICON, NVMe, and of course as well as SCSI. So NVMe basically hooks into the FCP layer, which allows FC NVMe to take advantage of existing HBA's devices and hardware performance acceleration. So then I'll hand it back over to Jay for a discussion on NVMe.
Great. Thank you very much. Obviously we want to have a reminder for Fibre Channel, and that was about as succinct as we can possibly make it. So let's see if we can try to do the same thing for NVMe. So in the beginning, non-volatile memory express, or NVMe, was designed to provide a standardized interface to PCIe attached storage. And part of the plan was to create a more efficient use of addressing non-volatile memory, which in turn provides low latency and high IOPS to direct attached storage. But it's only natural to want to extend the efficiency across a network. After all, storage has been accessed across a network for decades. The trick is, of course, to make the connections efficient while also staying agnostic to the transport type. So the NVMe Express group set out to define NVMe over fabrics to extend the efficiencies and model over a range of transport types. One of those defined fabrics is, of course, Fibre Channel. So let's do a quick breakdown of some of the main components and basics of NVMe. There are several places where you can find a thorough summary of NVMe and NVMe over fabrics. I know because I did some of them. But for now, let's summarize on some of the basic parts. The NVMe drivers for a PCIe-based system have been available in-box for all major operating systems for a few years now. Now, NVMe over fabrics will require its own specific drivers. Those drivers for FC NVMe will, of course, be provided by the Fibre Channel vendors, just like always. You have a Fibre Channel HBA that Craig was talking about, and those vendors will have their own FC NVMe drivers to make this whole thing work. Now, the other part that you'll need to have inside of an FC NVMe system is the NVMe subsystem itself. So this is going to contain all the architectural elements for the NVMe targets. It's the heart of what makes NVMe work, and it's made up of a number of different components. So let's take a look at them briefly. The first we're going to take a look at is the NVMe controller. And the NVMe controller is where all the NVMe commands are processed and creates and manages access to the namespaces and assigns a namespace ID, which associates the controller to the specific namespaces. Now, the controller acts as the endpoint of where the, in this particular case, where the Fibre Channel NVMe connection points are. So the ports that come in with FC NVMe are going to talk directly to an NVMe controller. Okay, so what is a namespace? Because we're talking about the NVMe controllers creating those namespaces. Well, a namespace defines the mapping of a physical media node to a formatted LBA range. So the namespace acts as effectively the aggregation of the NVMe, the non-volatile memory media that can then be associated to a logical block address, which in turn is then associated into a volume to the host. So an NVMe namespace, an NVMe subsystem could have multiple namespaces at the same time. The last part actually doesn't involve physical hardware, but it's still a very, very important piece of the puzzle. So NVMe works on the basis of queue pairs, which connect hosts to targets. In essence, you have three different queues. You have an administrative queue that is set up, that sets up the connection between the host and the NVMe subsystem. And that administrative queue directly interacts with FC NVMe, as we'll see in a little bit. And the I/O queues, which deal with the submission and the completion process. And this is the part where things become interesting, as each of these different queues have the interface into the types of storage network transports, which in turn facilitates those command and data transfers. Now, when we started NVMe, as I said before, it first starts out as a PCIe interface. And that PCIe interface defined how the queues were mapped, knowing that what you had was a shared memory model between a PCIe controller that was happening, that was implementing NVMe Express and a host. When we started looking at fabrics, and fabrics, by the way, is the shorthand for NVMe over fabrics. It's the kind of the shortcut abbreviation. We realized that fabrics are different than PCIe. Fabrics is more of a message-based transport where there is no shared memory between them. So what you see here in this diagram is PCIe on the left, which is a memory-based transport where commands and responses share the memory and then also the data transfer. In NVMe over fabrics, however, it's a message-based transport with no shared memory at all. Instead, it has a message exchange mechanism. And that may or may not have a data exchange mechanism as well. So these messages are called capsules. And Fibre Channel uses those capsules for both data and commands, whereas other transport mechanisms may not. So here we are, matching up the combination of these capsules and established queue pairs over a network. And each of the host and controller pairs have an independent set of NVMe queues. Because of that independence, they can scale consistently across the network, as well as scale to multiple subsystems. And one of the cool things about this is that each controller provides a separate set of queues rather than having a single set that needs to be that service multiple controllers. And obviously you can see how the conversation that Craig was talking about with the name server and with the multi-pathing, how it fits nicely with this kind of metaphor. So to that end, that brings us to how FC NVMe works. And it's up to Craig to take it away.
Thanks, Jay. So what are we going to look at here? I keep on repeating, we're looking at a high-level understanding about how FC NVMe works. You know, as any protocol, you start getting into the details, it can be pretty complicated, and there are definitely the complexities here, but we're not going to have time to go into that much depth in this talk. We're also going to try to understand how FCP can be used to map NVMe to Fibre Channel. So when we designed FC NVMe, we had some goals in mind. Of course, the first goal was that we wanted to comply with the NVMe over Fabric spec. And then, of course, the close follow-on to that is we wanted to have high performance and low latency. Also, we wanted to use existing HBA and switch hardware. We didn't want to require new ASICs or hardware to be designed to support FC NVMe. We also wanted the FC NVMe components to fit into the existing Fibre Channel infrastructure. This includes name server and things like that, and this allows us to continue the understanding that Fibre Channel administrators have about how things work with name server zoning and management. The performance goal means that we wanted to try to reuse existing hardware acceleration where possible. And since Fibre Channel does not have an RDMA protocol, FC NVMe chose to use FCP as a data transmission protocol. Currently, both SCSI and FICON use FCP for data transfers, and the reason for this is that FCP is deployed as a hardware accelerated layer in many HBAs. And like Fibre Channel, FCP is a connectionless protocol. Any connections are part of the upper layer of either SCSI, FC NVMe, or FICON. So how does FC NVMe map onto FCP? FC NVMe, the NVMe command response capsules are mapped into the FCP information units, and NVMe I/O operations are mapped into Fibre Channel exchanges. Let me show you how that works. So FC NVMe information units, which are basically Fibre Channel frames with FCP-specific headers added to them, are used to map the SQEs and the CQEs into a FCP command IU. So in this slide, if you want to send a command, the SQE, which is the submission queue entry, which is a NVMe command, is mapped into an FCP command IU. Any data resulting from that command is mapped into FCP data IUs. And then a response, which is the completion queue entry, is mapped into a FCP response IU. And then the I/O operations are mapped into exchanges. So for this example, a read operation would be a read command, data, and a response, and that's mapped into a single exchange. Or if you have a write command and its data and the response would be mapped into its own exchange. And this happens for any command, whether or not there's data, that you could have just a read, a command and a response with no data, and that would also be its own exchange. Another concept that's always important for any storage protocol is zero copy. Zero copy is when you minimize the number of copies the data takes place on the data before it reaches the user. Now, of course, ideally you want that to be zero. You always have a copy from the bus controller across the bus into the memory, but if you can get rid of any additional copies from there, you lower your latency. RDMA is defined to do that with a API that allows that actually enforces a way of programming that does zero copy. But you don't need RDMA to do that. Fibre Channel has had zero copy for years before there was an RDMA. In that case, data is basically transferred straight from the HBA into buffers that are passed to the user. And then for the FCP transactions on the wire, this slide's a little bit busy. It has some ladder diagrams on it. Really, this is sort of an example to show the difference between RDMA and FCP. If you look at the FCP transactions, and then you look at the RDMA transactions, the names have changed, but the process is the same. And that really is because in a lot of times in technology there are very few ways to do things right. And in this case, the fastest way to transfer this type of data is in a process similar to for both protocols.
So Craig, you're about to go into the discovery protocol, which I think is a good time to answer a couple questions that should have come in. It segues really nicely. So, when you go into the discovery protocol, one of the questions is, so there's no special HBAs or fiber channel switches required to support FC NVMe. And as we start to look at the discovery protocol, I think the answer will come out to me pretty clearly. But I'll let you answer the question. Do we need special HBAs or special fiber channel switches to support FC NVMe?
No, we don't. The current HPAs and switches can support NVMe. And it doesn't mean that some vendors may not have extensions that they add to devices, but their current devices can support it.
Right, and we've got somebody who's also thinking ahead. And since we're talking about the fiber channel protocol, which in turn can be run over Ethernet, this is the same for FCOE too, right?
Yes. Yeah.
Right.
Yeah. Everything we've talked about can run on FCOE as well.
That's right. And so I'll hold off on the next question until after the section. But thanks for stopping in and answering those questions at this point, because I think it fits with what you're about to talk about.
Okay. No problem. Okay. Into FC NVMe discovery. So for FC NVMe discovery, we take a dual layer approach. We use the Fibre Channel name server to identify the FC NVMe ports, and then we use the NVMe discovery service to disclose information about the subsystems on those ports. And this dual approach allows each component to manage the area it knows the most about. The Fibre Channel name server knows everything about Fibre Channel and everything about everything that's connected to Fabric. And the NVMe discovery service knows particulars about the subsystems. So an example here, if I was an FC initiator and I wanted to start talking FC NVMe, the first thing I would do is go out and ask the name server, or connect to the name server, and ask it, where can I find the NVMe discovery controllers? And it would give me a list of locations or ports in the Fabric to go look. Sorry. Hit the wrong button. Sorry about that. And then it would connect to those controllers. And those controllers would then tell me about the NVMe subsystems that exist out there. And once I have that information, I can then connect to those subsystems and start performing data transfers.
So basically, exactly the same way that it currently works.
That's right. The way it currently works, plus we also have the NVMe layer, which has the information that's specific to NVMe with the discovery controllers.
Right.
And then, of course, FC NVMe also works with existing services such as zoning, management server, and the other Fibre Channel services. And I did want to just quickly mention the demonstration that we had done this last summer at the 2016 Flash Memory Summit. We had a multi-vendor configuration, and there were actually a couple different. There are actually demonstrations at a couple different booths that had live Fibre Channel configurations, Fibre Channel hosts, initiators, talking to FC NVMe targets with a fiber channel switch in between. So with that, I'll pass it back to Jay.
Crap. See, this is one of those moments where you have to look down and make sure that you're off mute. Sorry about that. So the question, this is the perfect time to answer a question. And the first one that came in is, what does it mean practically that FCP is hardware accelerated by an HBA, which is something that you had touched on earlier.
Well, you know that in any piece of hardware that does, you know, a bus a connection from host to a certain network protocol, you have two ways of handling the data. You can do everything via firmware, and that means that the firmware is loading, setting up the DMA transfers, loading it into memory, handling the transmission, handling the responses, and then storing the data back into the memory. Or you can do a hardware accelerated platform where you have special designed hardware that takes care of the non-air, basically the regular paths. If you have air conditions, then that always goes back to firmware. But for the regular paths, you have specialized hardware, which is handling, setting up the commands, transferring the data in and out of memory and onto the wire. And you know the reason you do that is because if you have specialized hardware, you can accelerate and you can do those operations faster.
Right. And so we're getting a lot of questions about, you know, kind of a mixing and matching of how where the fiber channel kicks in and where the NVMe leads off. So to that end, you know, one of the questions that comes in is, you know, fiber channel buffer-to-buffer credits are still in play and nothing changes there. And the answer there is correct. That's correct. We're still using the lower layer fiber channel buffer-to-buffer credits, and if we're using FCOE, we'll be using clause frames underneath that at the Ethernet layer. So, so there's a question about how NVMe and whether or not it has a way to allow the initiator to tell the target to slow down to avoid slow drain. So the answer to that question, and Craig, if you want to chime in here afterwards, but the answer to that question is that that's a fiber channel issue. And any kind of facilitation for slow drain inside a fiber channel would be the answer to how to go about solving that particular problem. That's not less of an NVMe problem and less of an FC NVMe problem as it is a fiber channel problem. Did you want to add anything in there?
Yeah, that's at a network layer. It's not at the protocol layer, and it's something that has to be managed by the fiber channel switches and the fiber channel HBAs. Right.
So so to that end, speaking of a network issue, and wow, a whole bunch of questions just came in. I lost it. I lost the question. Where'd it go? Oh, here we go. So where we talked about discovery and NVMe discovery. The question is, where is the NVMe discovery controller living? And there's no discovery controller, and if I understand the question correctly. The same discovery protocol is used for FC NVMe as it is for regular fiber channel. So maybe I'm misunderstanding the question of it.
So let me answer that, Jay. The
sure.
discovery controller. So I think one key piece of information to keep in mind that in NVMe or NVMe over fabrics particularly, a controller is really a virtual construct. And a discovery controller is really a service that exists in an NVMe port. And it could be an NVMe port that has regular data subsystems in it, or it could be a standalone port that just has a discovery controller. And so the discovery controller can live in one or more of the NVMe ports on the fabric. There's a well-known name to attach to any controllers in NVMe, and also for Fibre Channel, the name server points to where those controllers live.
Right. So to that end, I just saw another question that came in that was appropriate. Oh, do you have to zone the NVMe discovery with all the NVMe hosts as well?
So for Fibre Channel, what we are recommending for in the FC NVMe standard is that if you have a Fibre Channel target port, that you should have a discovery controller on that port, so that that particular discovery controller can identify all the subsystems. So in that case, if you're following the recommendation in standard, you would have any ports you're talking to that's in your zone would also have a discovery controller in it to tell you what subsystems you can access from that port. And that's one of those layers of detail that I didn't go into because I didn't think we had enough time to go that much in depth into all the different details in that.
Right, and there is going to be an additional deeper dive for a lot of these questions as well, and we're going to use these questions to help guide us with that next step, I think. So one of the questions that comes in is that NVMe is in the Fibre Channel payload, and that is correct. And here's a question for you, Craig. Does FC NVMe improve bandwidth or just increase IOPS and lower latency?
That's a really good question. It's hard to answer across the board because it really depends on a particular vendor what their strengths are. In general, for Fibre Channel is a very high-speed, low-latency network to start with, and so Fibre Channel does have an advantage of being high-speed, low-latency, and with a lossless protocol. Is it going to be better or worse than any other aspect out there? I think that the answer is Fibre Channel has the advantage of being designed for storage, but the particular performance characteristics of any particular device, I can't generalize to say that any particular device is going to be faster or slower. I don't know if that answered that question properly or not. But.
No, I think it's a fair response actually, because there's still a lot of moving parts when we start to look at the NVMe over fabrics in particular, and especially architectural design will have a huge impact on overall performance, which is one of the reasons why Fibre Channel is actually one of the key fabric types, as a matter of fact. And come to think of it, that actually segues into the next section pretty well. So keep the questions coming, and we'll try to address them towards the end. Excellent questions, by the way. So obviously, we want to be able to talk about the details of technology and other stuff, but we also need to figure out why do we want to use it in the first place. And we were just starting alluding to that the architectural designs of Fibre Channel lend themselves pretty well to high-speed, dedicated storage networks like NVMe. So, aside from the technical merits, let's take a quick look at why this is particularly useful for Fibre Channel architectures. So with that, we present the top 5 reasons Fibre Channel NVMe might be the right choice. Yeah, I know it sounds like clickbait, doesn't it? Well, one of the things about NVMe over fabrics is that it is a new storage protocol technology. And there's an argument to be made that it makes sense to not have too many moving parts when implementing these technologies. So Fibre Channel itself is a well-understood quantity in the storage world. The architectural principles that we have been using for 20 years still apply. The benefit for high-speed dedicated networks is pretty obvious, at least it is to us. And there's a reason why 80% of flash storage systems use Fibre Channel as the protocol of choice, in terms of actual deployments in real-world situations. So for 2 decades, it's handled the most demanding kinds of traffic with an amazing track record. In other words, for customers who are trying to minimize the moving parts of a new storage paradigm, they may find that keeping the change down to one variable, like NVMe over Fabrics, will be something of a comfort. And one of the big concerns, item number 2, one of the big concerns about using new storage protocols is the question of whether or not you need to rip and replace what you have, or if you can simply add on the new traffic type to what you're already using. And you may recall that FTP is a layer of Fibre Channel that connects directly into NVMe and SCSI, which means that technically your existing Fibre Channel fabric can handle both types of traffic at the same time. Now I do say technically because there was a question that came in about supporting all the speeds like 4, 8, 16, and 32 gig. There is no reason technically why a lower speed would not work with FC NVMe. However, as we'll get to this in a second, you'll find out that qualification becomes extremely important, and the previous question about slow drain becomes extremely important. So that's just one star that's aligning, is to be able to have it at any particular speed. So I think what we will probably find is that because of the high throughput that NVMe has, there won't necessarily be a blanket statement that it was going to be supported on all different types of speeds. Okay, so that's a qualification and support question as opposed to a technical question. Nevertheless, you can still run NVMe and SCSI side by side with FC NVMe. Okay, so number 3. Fibre Channel's been around for a long time, and the nature of the fabric is that it knows every device that's connected. That makes the owner's job of discovering and controlling access to devices much easier, especially as you get bigger. And you're going to be hard-pressed to find someone who would argue that there's a system of storage fabric management as good as or as reliable as the Fibre Channel name service. Every Fibre Channel device from every manufacturer uses this method of discovery and fabric registration. At the moment, that kind of guarantee cannot be made for other transport systems. So, number 4. We're only able to talk about zoning briefly, and there were a couple of questions that were coming in about zoning and speeds. But it's important to remember that zoning and the added security benefits that come with it is built into Fibre Channel. So zoning controls and isolates the path in a fabric and can be used to ensure that only the correct authorized hosts obtain access to NVMe targets. And zoning also helps separate different environments, such as testing and production environments. It provides security by keeping users from accessing information, data, or even devices that they don't need or should not have access to. And FC NVMe inherits all of these benefits, and actually could be beneficial, especially when we start to talk about having the ability to run SCSI-based Fibre Channel and NVMe-based Fibre Channel on the same fabric. And last but not least, one of the most overlooked benefits of using Fibre Channel is the rich qualification process. So Fibre Channel solutions are qualified end-to-end, from operating system to storage target device. And manufacturers of Fibre Channel devices undergo a very painful, very expensive qualification and testing process so that you don't have to. And they do this to make sure that when a solution is implemented, customers will not have to struggle to find out on their own that incompatibilities have meant a very expensive stake. And this becomes really important as we start to understand new NVMe over Fabrics drivers, hardware, discovery protocols, and implementations. So the process will help put a lot of people at ease because the heavy lifting is already done for them and on their behalf. So with that, we've reached the end of the planned presentation, but I can see that there's been a few more questions that have come in. So let's see, is there anything that you saw, Craig, that you wanted to address?
Jay, why don't you start off? I'll look through them.
Okay. Okay. Let's see, we talked about that one. Can I run bidirectionally? SCSI Fibre Channel devices to Fibre Channel NVMe to SCSI Fibre Channel devices. I think that the question is really referring to translations as opposed to bidirectional. Fibre Channel is a full duplex protocol, and so you can run bidirectionally from the protocol perspective. But this sounds more like a translation question. The NVMe group has created a SCSI to NVMe translation layer and programming guide, and vendors would have to create some sort of handoff or translation. There's nothing in the standards that do that kind of translation for Fibre Channel to NVMe and back again. So there would have to be an independent vendor solution. More specific on a previous question, will Fibre Channel NVMe improve bandwidth to an NVMe array versus Fibre Channel to standard array of SSDs? So the question is really kind of in depth. I think we should probably put this on the to-do list for the in-depth one as well. And unfortunately, BrightTalk keeps moving around my screen. Bandwidth is very different than throughput. It's part of it, but it's not the entire equation. And so if you've got the encoding scheme for a 32 gig Fibre Channel link, that encoding scheme and that bandwidth remains static. So the question that needs to be answered is, does FC NVMe become much more efficient in using that encoding scheme? And there's nothing to compress or shrink within the protocols that actually make more work done in the same bandwidth space. All right, so the actual throughput and bandwidth will never change. It just has to do with the return to what's it called? It's called the return to idle is something that is often used as a measurement stick, and that is an endpoint solution. So how quickly can we actually return to an idle state where we can accept new commands? And that actually happens up at the upper level in NVMe rather than in the intersection between Fibre Channel and NVMe. The real answer to that question is, does the dedicated storage network over time provide you more work done using the same bandwidth elements? And that's where the architectural advantages of Fibre Channel and the oversubscription policies and best practices really can take a hold. Do you want to add anything, Greg?
So I think the aspect, the performance differences don't become because of the wire. The wire is as fast as it's going to be, no matter what protocol you run on it. It really is the ability of the device to respond and the ability of the stacks in the devices to move the data quickly. And when you're talking about all-flash SSD array that's talking NVMe, the idea is that with an NVMe protocol, that stack time and that device response time is lowered, and that's where you get the performance benefits.
Okay, well, on that note, and speaking about performance, there's a question that comes in that I think that's right up your alley. It says, I frequently see Fibre Channel ports transmitting at line rate, 8 gig or even 10 gig. So if the SCSI protocol can receive data at line rate, where does the performance improvement come from?
Yeah, so like I was just mentioning, it's really coming from the response time at the target and the initiator. Any one protocol on the wire, can only run as fast as the target initiator can process it. And the design goal of NVMe has been to minimize the amount of time that a target or initiator spends processing the data. And so that's where your your performance increase comes from. The line rate is going to be the same.
Great. I just thought it was worth reiterating.
So let me answer. There's a couple questions here. There's one about does NVMe support different QoS policies? And NVMe itself has some policies, but for Fibre Channel, so if you look at, we have two different layers, just like you have in SCSI. There's an NVMe layer and the Fibre Channel layer. For Fibre Channel layer, there are no additional QoS policies on the Fibre Channel layer than there is for over SCSI. Any Fibre Channel QoS concepts exist for both. I think a lot of these are NVMe questions and not really FC NVMe questions. There's also a couple questions about SCSI commands versus NVMe commands. Does the identify command in NVMe does identify command in NVMe is the same as SCSI inquiry? Well, this is not NVMe is not SCSI, so NVMe doesn't have inquiry commands. It doesn't have mode sense commands. It has commands that get the information about what the capabilities of the storage device are, but they're similar. It doesn't have the same mode sense inquiry commands as SCSI because it's not SCSI. And I know that sounds like a way of getting out of the question, but I think you have to really think in a different way. It's not a SCSI protocol. It's not a SCSI stack. There are ways of getting the information, but they don't have the same names. They don't have the same concepts.
Right. And we've got a lot of great questions, and I'm looking at the clock, realizing that we're not going to be able to get to them all.
Yeah, I see more getting piled on here.
Yeah, we're going to have our work cut out for us on that blog, that's for sure.
Yeah.
So some of the questions have to do with the status of vendor-specific availability, which unfortunately falls outside the scope of what we're talking about today. And different vendors are going to have their own ways of handling that. So I'm afraid we're not going to be able to answer those questions. There is one question that I would like to answer before we move on to just do a quick summary. And you've probably seen it too, Craig. So this goes over what we were originally talking about. Can you please explain more about the discovery and connectivity? So for example, in the question, when a Fibre Channel host discovers the NVMe controller, the NVMe discovery controller from the Fabric name service, is there a secondary recovery happening to further down the list for FC NVMe endports? Or the discovery controller is the only endport on the Fabric? And I think
actually that's a very good question, and that's one of those ones where you hear the phrase "a picture generates 1,000 words." Well, in general, a picture generates 1,000 questions. So the picture I drew is a very simplified overview of the process. And yes, you're right. The questioner is right. Once you identify the ports, there may be additional lookups in the name server to find out the Fibre Channel addresses of the NVMe data ports versus the NVMe discovery controller ports. And depending on whether or not they're on the same port as the discovery controller, or a single target device could have multiple ports. So one port could have the discovery controller, and you could have subsystems on the other ports, and so that it may give you a worldwide name that points to some other port, and then you'd have to go back to the name server to look that up and attach to that port. And I didn't put all that in that example because that's, you could spend 20 minutes talking about that alone if you really wanted to get in depth.
Mm-hmm. Yeah. But I didn't want to quite leave that kind of confusion behind because we did cover it. The rest of the questions, however, I'm afraid we're going to have to put off until the blog. But keep them coming, and we'll enter into the blog and make sure they get answered there. If you've got other questions or other comments, feel free to put them in there. We'll get to them, I promise, at least on the afterwards. If anything, we'll try to put some of the groups of the questions that are related into the next advanced FC NVMe session that it looks like there's a lot more interest than we were able to cover at the moment. So we threw a lot of stuff at you, and We hope that you were able to find some of it coherent. But to summarize, FC NVMe capitalizes on the speed and efficiency and performance of NVMe and NVMe over fabrics. The bandwidth questions notwithstanding, but adds its own value over the 20 years of storage networking pedigree. It allows customers to leverage existing environments so that they can be run side by side with new NVMe-based systems. And FC NVMe inherits the benefits and strengths of Fibre Channel architectures, including the trusted end-to-end qualification efforts that are well understood and expected by the industry. So, we are sorry that we couldn't get to all the questions, but as I mentioned at the beginning of the presentation, we will be posting a Q&A blog along with a copy of this presentation at fibrechannel.org. So we have several upcoming webinars that you might find interesting, and we will, of course, be announcing them not only on the website, but also via Twitter. So we do suggest that if you want to find out the fastest way of when the next one is, to follow the Twitter handle. It's not a high volume Twitter account by any means, so it's not going to be flooding your streams. And please don't forget to rate this webcast. We're constantly looking to improve and provide high quality content that is useful to you. So if you really like it or if you really don't like it, please feel free to be honest about your comments, especially if they're constructive, and we can actually do something about this. If there's like audio issues, we may not have too much of a hand in that. But thank you very much for your time. We certainly appreciate you giving us a moment to talk about Fibre Channel and NVMe. And we do hope you have a wonderful day. Is there anything you wanted to add, Greg?
No, I just thank everybody for tuning in.
Excellent. Again, thank you so much, everyone, and we do hope this was useful, and please help us be constructive as to what other things we can help you understand about Fibre Channel or Fibre Channel NVMe. Great, thank you.
Thanks. Bye.